Hello. I hope everyone is having a terrific Thursday. Today we're going to continue with relations, nearing the end of that. So we're going to be talking about some really useful theorems known as the modal laws or Dedekind theorems. We're gonna talk about seeing converse or transpose as an over approximation to inverse. So assignment 4 discusses the idea of how you can have approximated inverse using residuals, and it also discusses how to do it using converse. And so we're going to see that today in the setting of relations. Okay, so assignment 4 just introduced those abstractly, and today we're going to see them more concretely in the setting of relations or matrices or graphs. Before we get there, I would like to let you know that I've updated the cheat sheet yet again to include a bit more on residuals, just to summarize what you have from assignment 4, and just a bit more on these pseudo and semi-complements, and the fact that they really are just other examples of residuals. So just to point that out. For your convenience, we do have this translation from relation algebra to propositional logic, but it can be a bit daunting or overwhelming to see all of these and not know what they mean or what they denote. So I've added some possible interpretations here for you, and I've put them into gray text. So ideas for graphs, matrices, programs, right? So that might be helpful to some of you. It might not. So if you think of a relation as a graph, as a simple graph, then a relation that is a mapping and a bijection is really, it means your graph is a bunch of circles, right? That's all it is. You have a bunch of circles, or some circles might have one element and then a node, a self node. So that's all. Okay, dokes. Yes, so assignment 3 is due before midterm 5, but assignment 3 is I recommend you look at the recent homeworks on relations to really get you ready for midterm 5. Okay, so new things for midterm 5 would be, for example, stuff from here. This new page would be somewhat new. And here, okay. So set theory is all stuff that will be considered, and the next page of the cheat sheet. All right. So these are things that will be considered. Okay. Okay, dokes. So before we continue with the lesson plan, is there anything anyone wants to talk about in particular? So I'm going to go a little bit slower, and I'm going to try to repeat some stuff from the previous lectures, just to try to make sure it really sticks. Okay, so please ask questions if you didn't ask them the previous days. So we're going to see some similar stuff we already saw. I think it's helpful to have extra exposure, especially with the end of midterm busyness. So please let me know if you have any concerns. Okay. Will sequences be there in midterm 5? I recommend you look at assignment 4, and assignment 4 will answer your question. So please look at assignment 4 before midterm 5 on Tuesday. I highly recommend that. Okay. So the opening slide. How can you simplify if you know this? So this is back from assignment 2. Inclusions can be rendered as meets or as joins. Okay, so if we look at the cheat sheet right here, we have induced definition of inclusion. If you have an inclusion, A is included in B, then you know that A union B is just B, and A intersection B is just A. Okay, so if you know that P1 implies P2, then you know that the larger of them is going to be B2, and the smaller of them is going to be P1. Okay, so that's provided right here. Okay, so this is a very useful property to keep referring back to. Okay, and it works with OR, it works with union, it works with relational union, it works with maximum, it works with lowest common denominator, lowest common multiple. So a lot of things that satisfy the lattice interface. Okay, ducks. So please continue asking more questions. So assignment 4 mentions certain parts that may be relevant to midterm 5. Assignment 3 was primarily for the previous midterm, but we made the deadline later to avoid stressing people out. The thing to look at is assignment 4 right now. Give it a brief glance, please. It has some suggestions on things you want to know for the midterm. Okay, ducks. So let's continue here. Okay, so this is what I just said a moment ago, right? Unions, you get the bigger one, and intersections, you get the smaller one. Okay, and that's of course 357 and 360, or if you prefer, definition of implication. All right, so useful for upcoming assignments, homeworks, midterm, things to know this rule for. Okay. All right. So this rule shows up in 9.1 as set inclusion via union, set inclusion via intersection. So we've given it different names, but it's again the same rule, and we'll see it later again in the lecture. Please continue to ask questions. I do have my eye out on the chat. Okay, ducks. All right. So if there's anything in particular you really want to talk about, please do let me know, and we can pause from what we're doing and talk a bit more in depth. That's why we're reviewing some of the stuff from previous lecture. Okay, just really want everyone to be comfortable, and the idea is relations are really just sets of pairs. Okay, and sets are really just propositional logic all over again. So chapter 3. Okay, so it's really the same thing. But today we'll move into a little bit more on interesting properties of working with sets of pairs or relations. Okay, ducks. All right, let's bring that back there. So here's the translation I've posted for you down here, and we've seen a few times, and it essentially just says, hey, all these familiar looking symbols are really in terms of familiar looking symbols. Okay, this fancy arrow is really in terms of implication, right? So equality in terms of equivalence, right? This inclusion in terms of another inclusion. Okay, so hopefully you'll see that and be comfortable with it. Okay. The new features for relations are converse. Okay. So if you think of a relation as a graph, if you think of a relation as a graph, okay, then the converse of a relation is when you flip all the arrows in the graph. Okay. So if I have a graph and it has A to B, C, I'll just show you actually. I can draw. Let's do some drawing. So here's a graph. Oh, that's arrows. Sorry about that. Let me try again. So here's a graph, and it has 1, 2, and 3. Okay, and we know that 1 is like this, and we know like that. Okay. And 2 and 3 are left alone. Then the converse will have 1, 2, 3, and this one will now, this one will now point in the opposite direction, and this one will point in the opposite direction. Okay, so that's what I mean when I say if you think of if you think of a relation as a graph, then the converse is to flip all the arrows around. Okay, so I hope this makes it clear. Right, we have R right here, and then we flip the arrows around to get R converse. All right, are we all good? Can I hear some sound of approval or understanding? Just to make sure I haven't lost anyone yet.
We're good.
I'm sorry?
Good, sir.
Did anyone say anything?
Yeah, I said we're good.
All right, thank you. I don't know who that was, but I'm assuming it was Tammy, because there's a thumbs up. Was it not Tammy? Okay. That was Isra. Thank you, Isra. Another feature for relations is composition, right? If you think of a relation as a graph, then composition means doing the relation once is taking a single edge. Doing a composition means taking multiple edges. So R is one edge. R composed with R is two edges. R composed with R is three edges. And in general, this is a path or a reachability statement. So, and I've pointed to it down here for some examples in case you're interested. So hopefully we'll look at them in a moment. Okay, but I'm just trying to go over things we saw previously and just emphasize these different aspects so that way everyone's comfortable. All right. Then what is the domain of a relation? The domain is then all the nodes in the graph that have an outgoing edge from them. If you're somewhere in that node, you can go somewhere else. That's what it means to be in the domain. They're just all the edges, all the nodes with an outgoing edge. Okay, and this is very useful because if your graph, for example, denotes an automaton, a finite machine, which you may see next term, 2FA3. Then you want to know which states are not dead ends. Which ones can I get to and then I can move on, right? So which ones are in the domain of my relation, right? And then the range is all the nodes that have an incoming edge, right? So they're all the ones that can be reached from an earlier state, right? So when you have a state machine and you're like, can I ever get to that one? Oh, if it's in the range, then I can get to it by getting into a previous one. Okay, so really, and then if you think of them this way, then if something is in the domain of the flipped, that means it's in the range of the original, right? So a few of these properties suddenly take on a more intuitive feeling. If I have a graph and then I flip the arrows and then I flip them back, I have the original graph. All right. If my graph R is actually contained in a bigger graph S, then when I flip all the arrows, the smaller graph is going to be contained in the bigger graph when I flip all the arrows. So some of these things suddenly become obvious or intuitive. Okay, so I hope I'm communicating that. I hope you're understanding that. Please continue asking. Okay. So as mentioned the other day, composition is associative, as are most useful operators, and you take this axiomatically in assignment 4, and as you did in assignment 1, and it has an identity, which we call ID, right? And two things are related by the identity if they are identical. Okay, so they're the same, right? And that's what we have right here. They're related by identity precisely when they're identical. Okay. So for preparing for the midterm, it would be really nice to try to prove these using the definitions. Using this as definition for composition and using this as definition for identity. And you have some definitions over here for equality to actually be able to prove that the identity is the identity. Okay, so some stuff to ready. If you struggle to prove these, you really need to study a bit more for the midterm, and please ask and make use of course help. So you should definitely be able to prove these two for the midterm. Okay. So in general, most of the theorems we see, it's good practice to prove them. All right. So here's an interesting relationship between composition and union, and because of the feedback we received, we were just going to throw more stuff into assignment 4, and we were going to say, hey, composition distributes over joins, but we didn't want it to be too long, and so you'll see some stuff that we didn't put in the assignment. Okay, so if you do one thing, if you do Q, then you decide. So remember, we have agreed to call this symbol, this composition, we have agreed to call it and then. There is a translation between symbols and English in assignment 4, where we agree to name these things useful names and how to interpret them in terms of fashion, right? Because fashion is fun and it might make you feel better to learn about clothes in the math class. So if I do Q and then I decide to do R or S, that's the same thing as doing Q and then R or Q and then S. Right, it's like multiplication distributes over addition, right? And I'm here and then I get to B, and then I can decide I can do R to get to C or S to get to C. So really I have the top option or the bottom option. Okay, so alrighty. So and as you've seen before, multiplication is a monotonic, conjunction, meets, joins, or many operations are monotonic, and likewise composition is monotonic. So there is an interesting thing here. If you notice, we're proving Q and then S is contained in R and then S, all right, provided Q is contained in R. And here's something new. We've usually just unfolded the definition. We're like, what does this fat semicolon mean? And we're like, oh, it means use in existence. And what does this inclusion mean? It means use a for all, and then implication. And now we have a really long formula. If you try to unfold this, this is a for all xy, and then over here you have an exist z, and then over here you have another exist z prime. So that's around 4 quantifiers. So that's a lot to keep in your head, and it will flow off the page. It's too long, all right? But remember we said, hey, inclusions can be thought of as meets or joins, right? So let me momentarily go back here. We said inclusions can be thought of as meets or as joins, right? And so that's what we'll do here. We'll start off with the bigger side, right? Then we'll realize, wait a minute, I know that Q is contained in R, and the way I'm going to use that is as a join, and I get here. Then I know that composition distributes over join, so I can simplify. And then just as you've seen before, A or B is contained in A, right? This is the weakening, strengthening laws, which are, again, right here, right? So we have these weakening, strengthening laws that tell us how joins are related to individual operands, okay? So with that in hand, we're done, right? So if without using these properties, going brute force is very painful. Okay, so just pause for a moment to write that down. All right, brute unfolding. It's painful. So is there any questions in particular about this proof right now? Does anyone have any concerns or queries? Does anyone know what we're talking about? Is anyone there?
Yeah, we're here.
People are responding in the
Okay,
chat.
all right. I'm getting all the texts
Yeah.
now. Thank you. Yes, all good. All right, good to make sure. That's fine. Please do take a moment to process. That's why I'm trying to be consciously taking breaks to give you the opportunity to ask. So someone just mentioned the strengthening part, and they're not really sure what happened. So just if you look on the right side over here, we have this part, right? So we have some strengthening parts right there, right? And that's what we're trying to do here. We're saying we have this left part. Let's get rid of that. We're saying we have this left part, and we have a right part, and we're just going to drop one of them. We're making so we can have either this or this, and we're going to say, you know what, we're going to strengthen, and we're just going to choose that. Okay, so if you read this formula, you say I have S or T, and I'm going to strengthen. I'm going to say, you know what, let me just have S. Okay, if I have S, then I have S or T. Okay, so this is weakening strengthening laws 376 and friends. Okay, and we see them again here in set theory 1131. So this is just assuming. We're assuming this part because we're proving an implication. And if you recall, using the relaxed proof style of chapter 4, which has been in effect since midterm 3, assuming means I have this, and now I just need to prove this part. Okay, next. Alrighty then. So now for a moment, when we look at a diagram, let's think whenever there's a fork in the road, it means I have to do both. Okay, when there's a fork in the road, I have to do both. So here, I have to do Q, and then I have to do both R and S. Okay, I need to do both of these things. Okay, well, if I have to do both of these things, that's like saying, all right, I can do Q and R, and I can do Q and S. I can, you know, if I'm going to do Q and then I'm going to do two things, that's like doing Q in the first one and Q in the second one. Okay, so that's the first rule right here. Okay, notice, unlike composition and with join, this is not an equality. They're not equal. Okay, the reason they're not equal is, for example, if I can do this, Q and then R and Q and then S, I might not be able to do Q and then R and S together. Okay, R and S might not be doable together, but doing Q and R and Q and S might be doable. So for example, down here we're saying there's a person that happens to be my neighbor, and that person is both the brother of and the parent of C. That sounds really impossible. But if this is the case, then that means there's a person who is my neighbor, and that person is the brother of C. Okay, so to the left of me, there's a neighbor who is the brother of C. Okay, so C's brother is my neighbor to the left of me. And then to the right of me, there's a neighbor that happens to be the parent of C. That sounds doable. Right? I can have two neighbors, and one neighbor can be C's brother, and the other neighbor can be C's parent. That sounds very doable. But if I have C's brother as my left neighbor and C's parent as my right neighbor, that does not mean I have a neighbor which happens to be both C's brother and C's parent. All right, like it's biology has a say in that. Can't be the parent and the sibling at the same time. So that's why it's an implication. You know? If you have this unusual situation, you can have this more realistic situation. And if you have this more realistic situation, you're not going to have this unusual situation. Okay, so that's why it's an inclusion, and this unusual situation has been chosen to demonstrate, hey, you can't go from here to the other side. That's why it's strictly weakening. The other side is just might not be compatible, right? Like being a brother of someone and a parent of someone, that's the empty relation, if we choose to define it that way. And then this is not possible, but this one is, right? So things to be aware about, okay? So let's get back to talking about more properties, right? So if you think of a graph as being a relation, then its reflexive means every dot has a loop to it. Irreflexive means that never happens. Symmetric means if you change the order of the arrows, it's the same graph. That means really the graph is undirected, right? The order, the direction doesn't matter, okay? Anti-symmetric means there's at most one arrow, and here I've written these down here actually for you. Okay, so anti-symmetric means mutually related nodes are necessarily self-loops, right? So you are welcome to consult that as needed, right? And asymmetric means you can have at most one edge between any two nodes, right? So I leave you to read that if you like. The interesting thing of looking at these formulations is that the relation algebra is really, really terse, so small, but these ones are so long. This one, idempotent, we're not even going to write it down for you because it's long and not helpful, right? To write it down, it's going to be a for all x, y, and then we're going to have an exist z, and then we're going to have an equivalence, and it's just a big mess, not very helpful. But if you think down here, right, idempotent just means the lengths of paths can be arbitrarily, right? So if I have a graph and I have a path of length 10 between this node and that node, okay, I can shrink that down to a path of length 1. Then I can increase that to a path of length 3, right? So you can change as you like. Right? That sounds like a useful property to have, right? You know, so that's pretty neat. Okay. And we've talked about orders before. We said if it's a reflexive, transitive, and anti-symmetric relation, it's called an order. It's strict if it's irreflexive, like strictly less than. Oh, did not mean to do that. Okay, like strict less than, right? So and we say it's an equivalence relation or a similarity relation if it's reflexive, transitive, and symmetric. Okay, so these are words you'll likely keep seeing again and again in computing and software. Okay. So another way to, of course, see graphs is as matrices. Matrices that have a 0 or 1 in the elements, or if you like, they can be either turned on or turned off in this graph right here. Okay. Notice this graph is for the divisibility order from assignment 2. From assignment 2, we talked about divisibility, and being reflexive means the diagonal is all there. So the diagonal is all turned on. So here's the diagonal, it's all turned on. That's what it means to be reflexive, okay? To have everything turned on means it's the least element. 1 divides everything, okay? So you can glean quickly some interesting properties from matrices and from graphs if you look at them this way, right? Here is another one. This one is for a power set, right? And this graph, right, it has the empty set at the bottom, and it has the universal set at the top, right? And then relationships are as you go, right, upwards. Okay. In both of these, we're not drawing all the self loops. Just otherwise, it would be a mess to look at. But there are self loops because they're reflexive relations. Okay, and that's captured by having them in the diagonal. Okay, does. So here is a proof that I tried to show really quickly last time. Right? If you have a relation that's reflexive, then its converse is also going to be reflexive. And for a moment, let's forget about the algebra. We said a relation is a simple graph, so a bunch of dots and lines between them. The converse means change the direction of each line. Edge, change its direction. So if it's reflexive, that means every dot has a loop to itself, okay? Now, if we change the direction, well, a loop pointing to itself is just a loop pointing to itself. And so the resulting graph will have loops for every node, and so it's reflexive, okay? Likewise for transitive, right? Transitive means if there's ever a path of length 2, then I can turn that into a path of length 1. And if I change perspective and the arrows face the other way around, I have a path of length 2, and I can make it into a path of length 1. Okay, so you can have a visual appeal to these set theoretic operations. Okay. Please do ask questions for things that may not make sense. Okay. Want everyone to do really well on the upcoming midterm. Okay. Here is another theorem. Reflexive and transitive implies idempotent. Okay. So remember, transitive means if you have a length 2 path, you can squeeze that down into a length 1 path. Transitive, a reflexive means every node has a length 0 path, right? So you're a path from X to X is just a self loop, okay? Well, if you can always squeeze length 2 paths down to 1, and you already have length 0 paths, then idempotent says you can squeeze any length path you want down, right? And the proof is really simple, right? Using the algebraic formulation, right? We already know that R is contained in R times R because that's what transitivity is. So all we need to do is show the converse, right? So this is the only one we need to show. We start off with R, we use the identity, we know the operation is monotonic, and we already have reflexivity, which says identity is contained in R, and we're done. It's a 3-line proof. If you try to use the for all exists implications, it's a mess. It's just a terrible, terrible, horrendous mess. Somebody asks, what does the word for any mean? This colon just means a type, okay? So when we're talking about the identities contained in R, we're saying for every node B in the collection of nodes we have, we're referring to, so all the dots on the page, that dot is going to be related to itself, right? So if I have a dot B, then that dot is related to itself. So I have a loop to it, a self loop. Okay, ducks? Good questions. Please continue asking more. Okay. You're welcome. Please ask more. So this is really why we're talking about relations, right? Proofs with quantifiers suddenly become so small and so cute and easy to read and don't flow off the side of the page. Okay, so if you look on the right side here in the cheat sheet, just trying to read these things can get longer and longer. Like here I give you the explicit formula, but then down here I just give up and say I'm not going to give you any more formula. It's too long. Like I would run out of space, so I'm just not going to give you this. It's too long, right? And likewise even here, I'm like it's not, the formula is not insightful and there's nothing to get from it. I'm just not going to show it to you. The formulas get longer and longer with quantifiers, so using relations really helps. Okay, ducks. Let's bring that there. Yeah. So I hope everyone is comfortable with the idea of a simple graph. Okay, just a bunch of dots and lines between them. All right, nothing too deep. But you know, it's like having cities and then at most one highway between any two towns, right? Or you work in a company and the people are called the nodes or the vertices, and the supervisor relationship is the edges. I report to Jim, so there's an arrow from me to Jim. I also report to Monica, so there's an arrow from me to Monica. Monica reports to herself, there's a self loop, and Jim reports to Ibrahim, and so there's an arrow from Jim to Ibrahim, right? So you have multiple arrows, right? So it's just a drawing. Okie dokes. So the benefit of realizing, hey, relations, let us talk about these graphs. and they also let us talk about matrices and programs, all right, and sets. So it's relations are just, you know, like everything's there, the cream of the crop. All right. So all that stuff from assignment 2, assignment 1, assignment 3, assignment 4, all that relation order stuff we were doing and divisibility, and it's all available to us now. All right. Before we didn't have access to these, so we get everything now. It's great. Okay. So a moment ago I was talking. I said if you think of a relation R as a graph, then to say X is related to Y via R means there's an edge from X to Y. And if you say, oh, X is related to Y by R times R, so R and then R, it means I start at X, then I do one edge, and then I do another edge. Okay, so that's why we call it and then composition. So X, and then I do one step, and then I do another step, and now I'm at Y. So it's a two-step path. And that's what we're saying here. So here, this example says we have a three-step path. Okay, so maybe let me try and zoom in just like that. Okay, so this is called a three-step path. Okay. Remember, we said the domain is all the reachable, all the nodes that have an edge going out of them, right? Not being inside the domain is a special term called a sink, right? The range is all the stuff that you can get to, right? So the range is all the things that have an incoming edge, and not being inside the range means you're a source. Okay. So let's look at natural numbers. So recall from a few lectures back, we said if you have a type, you use low floor brackets to treat it as a set. So our set is all the natural numbers, and we've mentioned this before, where you use upper corner brackets to treat a function as a relation. Okay, so there's an edge between any two pieces if the second piece is the successor of the first piece. So 2 is 1 plus 1, so there's an arrow here. 5 is 4 plus 1, so there's an arrow here. And this is in general a very boring graph. It's just a straight line. Okay. Notice there are no self loops because 0 is not the successor of 0, and there is no. And this is also not transitive because I have a length 2 path right here. 2 is reachable from 0 by going one step and then go. Okay, so there's a 2-step path to get from 0 to 2, but I can't get from 0 to 2 in one step, so it's not transitive. Okay, dokes. So and of course we would write it like this. There is a 3-step path to get from 2 to 5 because 2 plus 3 is 5. Right? So very boring example, but just to try to get this across. Okay. We said that when you have, if you take a graph and you apply the converse operation, so you flip all the arrows, nothing changes, then that means the graph is undirected. Okay. So look at this graph right here. Right? If I apply the converse operation, the relationship between Z and Y does not change, right? This one gets flipped around and essentially becomes that one, and this one gets flipped around and essentially becomes that one. So just focusing on Y and Z, there's no change. But if you look at X and Y and you flip it around, this says Y reports to X, or Y is below X. If you flip it around, it says X is below Y, right? So that matters. So when a graph is undirected, flipping the arrows doesn't matter. We usually don't use arrows at all. We just draw a line without any pointy part to it. Okay. And so sometimes you say, all right, I have a graph. What does it? I have a relation that denotes a graph. What is the corresponding relation that denotes the undirected graph? Like, I don't care about direction. I have this graph and I don't really care about direction. I want to treat this graph as a relation and I just don't care about direction. What do I do? And that problem is solved by talking about symmetric closure, right? So I have a graph R, and I want another graph Q, okay? And I want this graph Q to be symmetric, okay? Then, for any other graph that is also symmetric, for any other graph P that is also symmetric, I want it to contain Q. That's a mouthful. So the easiest way to say it is, I want Q to be the smallest symmetric relation containing R, okay? So I have a relation R, and I'm saying, oh, this relation is directed. That's super lame. I wish it wasn't directed. So I want a symmetric relation that contains R, okay? So I have my relation. Let me add in a few more pieces, a few more edges to make it symmetric, but not too many. And that's why we're saying it's the smallest one. I want the smallest symmetric relation containing R, okay? Incidentally, you just need to add in all the reverse arrows. All the arrows that are missing, you just add them in. And so the symmetric closure is just says, hey, add in all the missing parts. So if we start here, this one, we said X and Y, when you flip it, things break. So let's add in the missing parts. We add in that missing part and the other missing parts, okay? And now if there's an arrow this way and that way, when there's multiple arrows, right, in multiple directions, instead of drawing both of them, we just draw a single undirected one, no triangle head at the end, and then we get this. Okay, so this relation algebra stuff seems to be very useful to graph theory. Well, look at that. Ain't that neat? Okay. Are there any questions? I'll take another moment to see if anyone has questions or concerns. I just want to make sure people are learning and we're not going too fast. Does anybody want to make a remark? That makes sense. Okay, good. Somebody asks, what does this mean? It's literally you grab a piece of paper, which I totally have access to. Okay. So you grab a piece of paper, right? So here's an empty piece of paper, and then you draw some dots on them. A, B, C. So here's some dots. Okay. So these are your nodes. The dots you decide to draw down are your nodes. Okie dokes. Then you say, hey, I'm gonna have some arrows like this, like that. Okay. So here are some arrows between them. Okay. So and that's it. I just made a drawing. I'm not a great artist. And this is what I did, and this is called a graph. Okay, so the arrow part just says I'm going from A to B. It's a one-way. Okay, it's a one-way street. Like Hamilton downtown has a lot of one-way streets. Okay, so imagine the dots. The dots are buildings. Okay, and the directed arrows are one-way streets. Okay, so I can go from A to B. There's a one-way street. I can go from C to B, there's a one-way street, and I can go from A to A by going in a court. There's a court or crescent, for example. Okay, so that's all that they denote. Good question, right? They just denote a directed relationship, okay, and that the direction matters. It's like when you have a pair, and then the pair is ordered, and the ordering matters, okay? If you don't care about ordering, for example, you live in a city where all the streets are two-way streets, then you would consider an undirected graph. You would say, let me model my city using an undirected graph. So it's like when we talked about sequences. It depends on the problem you're working with. If your problem requires a collection of things, then you can pick between a set or a sequence. If you have people coming in to buy coffee at Tim Hortons, then the order that the people come in really, really matters. The first person to come in should get their order first. Okay, so I would use a sequence to model people coming to Tim Hortons to buy coffee. I would not use a set because a set ignores order and multiplicity. Okay, so it says whether you decide to have dots and directed arrows or undirected arrows depends on the problem you're modeling. Okay, and you'll see applications of these hopefully in 2FA3 next term, and in the automata class you'll take in third year. But relations or simple graphs are ubiquitous. They're just everywhere. Okay, that's why we're spending a little bit more time on them than you would think. Okay, you're welcome. Please ask. Somebody said Moore state. Yeah. So Mealy machines, Moore machines, finite automata. Think, hey, I'm right here at X, and then I can do something to get to Z. So a change in state. But I can go from X to Z only. Whereas if it's undirected, I can go this way or that way. It doesn't matter. Okay, it's like having equality. Equality means I can use left-hand side equals right-hand side, or right-hand side equals left-hand side. But if you have a less than or equal to, then they're not replaceable. You can't replace each one and have an equality. The moment you decide to replace one, you have to worry about using monotonicity laws instead of equals for equals Leibniz laws. Good question. You're welcome. Please ask more questions. Okay. So assignment 4 talks about converse as being an over approximation of inverse. And that's the whole premises of assignment 4. And we work using division operators, and then we say, hey, what about when you reverse a list? Reversing a list is almost like undoing it, kind of, approximately. And that's the goal of assignment 4. Assignment 4 tries to work up why you would care about converse by mentioning reverse. Okay. So here, I can go from Q, then R, and at the same time I do S. Right. So we're doing them together. Right. That's the same thing as saying, okay, I can go from Q and R, and at the same time I'll just forget. Right. So I went from I did from Q and then R, and then I did S. But then I did Q and R, and here's what I forgot. I forgot that C and C prime are the same. Okay, so I've weakened what I know. All right, I forgot that C and C prime are the same. I have this triangle, and now I forgot the relationship between these intermediary pieces. Okay, and the idea is you can think, hey, Q times R, and this Q times Q inverse, Q converse, they cancel out and you just get S. Okay. Of course, they don't always cancel out. So this modal rule is true in general, but because they don't always cancel out, this is an inclusion and not an equality. Okay. So here is another way to make it an equality, though. If you recall at the very beginning, and as mentioned in the cheat sheet, whenever you have an inclusion, you can make that into an equality, right? And so we can take the modal rule inclusions and lift them into equalities at the cost of introducing an additional intersect S. Okay, so these modal rules are just very useful theorems like 332 or 362 or 364, just useful theorems for you to know. They can be very helpful. So let me show you an example. When you fuse the rules together, the fusion of these rules is called the Dedekind rule. Okay, so that's a nice way if you don't like to work with these independent parts. Right here, you start with the left, and then you factor out Q to get this one. Right, you factor out Q, and this one you start here, and then you factor out R. You pull out R. Okay. So, and we talk a bit more about this in assignment 4, okay? But it's sufficiently important that we thought, let's bring this to lecture. Okay, and then when you decide to pull both of them out, you get this intricate formula. And depending on which one you use, it can make life easier. Okay, so they're useful to know, all right? And just as before, if you have a triangle, I do Q, then I do R, and at the same time I do S. Like saying, all right, I'll do the first one and the second one, and I forgot about the relationship right here, right? Is the boxed A the same as the original A? Is the boxed C the same as the original C? I forgot this additional information, and that's why it's an inclusion. You forget, right? You use existence introduction to prove these theorems. Okay, so I'm running out of time, so I'll just wrap up real quick. I just want to mention again, you can make it into an inclusion. You can make it into an equality by using this handy dandy rule we've mentioned before. And I just want to show you one example. So here is, do I have time to show you an example? I'm running a bit out of time. We'll just stop and I'll show you an example tomorrow. All right, no need to rush into it. So I hope you had a good lecture, and I'll stick around and answer questions. But everyone else is free to go, and have a terrific Thursday. I'll see you tomorrow. We have some questions. Okay, let's see here.